Hello everyone and welcome to today's lecture. Today's lecture will be on Taylor series expansions and how to find the Taylor series expansions of many different types of functions. So the main idea with Taylor series is that we say that the Taylor series of a function is an infinite power series expansion representation for a given function. Specifically, we want to ask the following question. Let's say given a function f of x, under what conditions and on what intervals for that function f of x can we express f of x as an infinite power series, which were talked about and introduced last lecture. So when can we express f of x as some summation of coefficients times powers of x minus x naught, where x naught is the center of the power series. So we know that in general a power series is going to converge when x minus x naught is less than r, or within a certain radius of convergence. And it turns out that we can actually go through and derive a very nice, very general formula for CK. So how to do this? And the idea is we do this in the following manner. If f of x is c naught plus c1 times x minus x naught plus c2 times x minus x naught squared, and so on and so forth. In all of this, we're assuming that x is within the radius of convergence. So if this is true, and we know that x is within the radius of convergence, then we know from the last theorem in the last lecture that we can differentiate the series term by term. So if f is a differentiable function, the derivative of this function is going to be the derivative of this entire sum, term by term. The derivative of c naught is 0. The x derivative of this expression is just going to be c1 plus c2 times x minus x naught, or 2 times c2 x minus x naught plus 3 times x minus x naught squared, and so on and so forth. Likewise, if we take the second derivative of the function, if that is possible, this is going to be equal to 2 times c2 plus 3 times 2 times x minus x naught plus 4 times 3 times x minus x naught squared, and so on and so forth. This is the second derivative. And we can continue this procedure however far f is differentiable. So like the third derivative of both sides of this expression right here, we'll get 3 times 2 times, oops, and I just realized that we need a C3 right here and a C4 right there, because I'm going a little bit too fast here. This is C3 and this will be C4. And we need also a C3 up here in this expression as well. So when we take the third derivative, the derivative of this is 0. The derivative of this is going to be 3 times 2 times C3 plus 4 times 3 times 2 times C4 times x minus x naught plus 5 times 4 times 3 times C5 times x minus x naught, and so on and so forth. So in general, what we're seeing here is that the kth derivative of this expression, if we can take that many derivatives of f, is going to be equal to k times k minus 1 times k minus 2 all the way down to 1 times ck plus by the way, this is just k factorial plus k plus 1 factorial times ck plus 1 times x minus x naught plus all of the higher order terms if that we have in this series expansion. And this directly gives us the correct way of figuring out what the kth coefficient is, because the formula that we've derived and that we figured out is that this is that fk, the kth derivative at the point x, is just going to be k factorial, or the multiplication of all the numbers up to k, times ck plus all of the higher order terms. So this is, say, like k plus 1 factorial times ck plus 1 times x minus x naught plus everything else in the Taylor series expansion. And everything in the higher order expansion is going to be x minus x naught raised to a certain power. So the way of figuring out what ck is, a formula for ck, is if we plug the value x naught into the function, we get that the kth derivative of the function f at x naught is going to be k factorial times ck plus, well, x naught minus x naught is 0, and because of that, all of the other terms in the Taylor series expansion are also going to be 0, all the way up to positive infinity. So this gives us a direct formula for ck. The kth coefficient in a Taylor series expansion is the kth derivative of the function at x naught divided by k factorial. And there you have it. This is the correct way for any function that has infinitely many derivatives, the correct way of getting the kth Taylor coefficient. Now, we'll go into exactly what's necessary in order for finding the Taylor series expansion of a function with less than a certain number of derivatives. This is possible to do. It's also possible to get very accurate bounds on the error in a given Taylor series expansion. But the idea here is that this gives us exactly what we need for finding the Taylor series expansion of any function for which we can take the derivative of the function, or many derivatives of the function. And what this allows us to do is construct a power series representation for any functions, no matter how complicated they may be, as long as we can do this. So let's start with a relatively standard example. We'll look at the function e to the x, and we'll do this around the expansion point of 0. So the center of the power series is 0. By the way, when we do this around 0, when we do a Taylor series expansion around 0, this is sometimes called the Maclaurin series expansion. So you might see the word Maclaurin series in any calculus book that you're reading. This is just the normal Taylor series, but around 0, expanded around the point 0, x naught equals 0. So to do this, we have to use Taylor's formula for the derivative. And the idea is that in general, this is relatively, it's a relatively straightforward procedure for relatively simple functions. So in this case, the 0th order derivative of this function, or f prime of x, it's just the 0th order derivative is no derivatives at all, so it's just the function itself. The first order derivative of this function is the derivative f prime of x. And for the exponential function, that's just e to the x. The second derivative of this function, or f double prime of x, is also going to be e to the x. And you can see very clearly that for the function e to the x, the kth derivative of this function, or the derivative k times, is just always going to be equal to e to the x, because the derivative of e to the x is in fact always equal to itself. It's e to the x. So what that means is that at the expansion point, x naught equals 0, the 0th order derivative of the function, of our function, or the function itself, is just equal to e to the 0, or 1. The first order derivative of our function is equal to this at 0, which is e to the 0, or 1. The second order derivative of the function is e to the 0, or 1, and so on and so forth, all the way down the line. So the kth derivative of this function, e to the x, is just going to be e to the 0, which is 1, for any order of derivative we want. And so the formula for the Taylor series coefficients, ck, is just going to be this value of the kth derivative at the expansion point, which is 0, divided by k factorial, or 1 over k factorial. And our Taylor series for e to the x is exactly equal to the summation from k equals 0 to infinity of this coefficient ck, which is 1 over k factorial times x to the k. And this is the power series expansion for the function e to the x. So this is a very, very powerful tool. We've seen that this formula can be directly applied, and we have to be very careful as well, because we want to make sure that we're within the radius of convergence. What's nice is that we have our direct formula for determining the radius of convergence, which is that this is the limit as k goes to infinity of the absolute value of ck over ck plus 1. This is from the previous lecture on power series. This is the limit as k goes to infinity of 1 over k factorial over 1 over k plus 1 factorial. These are both positives. The absolute value here doesn't really matter. This is the limit as k goes to infinity of k plus 1 factorial over k factorial which is the limit as k goes to infinity. And remember, k plus 1 factorial over k factorial is just going to be equal to k plus 1, because k plus 1 factorial is the same thing as k plus 1 times k factorial. Divided by k factorial. So this limit is the same thing as the limit as k goes to infinity of k plus 1, or positive infinity. Which is very, very good, because what it tells us is that this Taylor series expansion is actually valid for every single value of x. The radius of convergence is, in some sense, the entire real number line, because it extends across the entire real number line, because this will converge. The series will converge for every single value of x. No matter where x is, it's within the radius of convergence of this function, right? Because for any value of x, the absolute value of x will always be less than positive infinity. Let's do another example function. We'll do one more. Specifically, we'll choose f of x is equal to cosine of x. So to get the coefficients, the Taylor coefficients, you have to take this function cosine of x and consider what the derivatives of this function are going to be. And we'll do this Taylor series expansion around the point 0 as well. So we'll do the Maclaurin series expansion. Derivative of cosine of x is negative sine of x. The second derivative of cosine of x is the derivative of negative sine of x, which will be negative cosine of x. The third derivative will be the derivative of negative cosine of x, which is negative times negative sine of x, or positive sine of x. And lastly, the fourth derivative will be the derivative of sine of x, which is cosine of x. And this process just continues to repeat. So at the point x naught equals 0, you have that f of 0 is equal to cosine of 0, which is 1. F prime of 0 is negative sine of 0, which is 0. F double prime of 0 is equal to negative cosine of 0, which is negative 1. The third derivative, f triple prime of 0, is equal to sine of 0, which is 0. The fourth derivative at 0 is going to be cosine of 0, which is 1 again. And it's not too hard to see that this pattern is going to keep repeating. So the kth derivative of the function at 0 is going to be equal to 0 if k is odd, and it's going to be equal to negative 1 to the k. I will say it'll oscillate between negative 1 and positive 1, so it'll be negative 1 if k is equal to make a little bit more room here. So negative 1 if k is equal to two, 5, and so on and so forth. And it's positive 1 if k is equal to 1, or k is equal to 0, if k is equal to 4, and so on and so forth. Oops, this should be 6 right here, not 5. If k is equal to 0, it's positive 1. If k is equal to 2, it's negative 1. And k is equal to 4, it's positive 1, and so on and so forth. So it oscillates in some sense with k as you get for larger and larger and larger values of k. So what this means is that the Taylor series coefficients are similarly defined. The Taylor series coefficients, ck, are going to be 0 when k is odd, going to be negative 1 when k is 2, 6, and so on and so forth. So the next term up will be 8, and so on and so forth, or 10, and so on and so forth. Likewise, it's positive 1 when k is 0, when k is 4, when k is 8, and so on and so forth. Which means that our Taylor series for the cosine function is going to be the following. It'll be cosine at 0 plus and we also need that ck, remember, is the derivative over k factorial, so you have to include k factorial here as well. So it'll be when k is equal to 0, k factorial is 1, so it'll be 1, and then it'll be minus 1 over 2 factorial times x squared plus 1 over 4 factorial times x to the 4th. The next one up is minus 1 over 6 factorial times x to the 6th. and so on and so forth. So it's incredible that this will convert. This actually converges to the cosine function. And it turns out that just like before for the exponential function, you can go through and show that the radius of convergence for this function is also positive infinity. So for every single value of x, no matter where it lies on the axis, this infinite series will in fact converge. So another way of writing this is a closed form way of writing the sum using our sum notation. You could write this as cosine of x is the summation from k equals 0. Now I'll use a different index than k because we kind of used that before. From I equals 0 to infinity of negative 1 to the I times x to the 2i over 2i factorial. So this series is the same as this series right here, but it's a closed form way of writing it with our summation notation, which is much more helpful. It's very, very helpful. Similarly, we can go through and do the exact same thing for the sine function. I recommend you going through and doing that yourself, but it turns out that when you go through and get the expression for the sine function, the Taylor series expansion for the sine function is very, very similar around this for sine of x around x naught equals 0. It's going to be the sum from I equals 0 to infinity, negative 1 to the I times x to the 2i plus 1 over 2i plus 1 factorial. It'd be good practice to go through and show that, just like we went through and did that for the cosine function. But this is the correct way of going through and dealing with the Taylor series expansion. By the way, the radius of convergence for this one is also going to be positive infinity. So you can show this using the ratio test, just like we did before, which is very, very neat. So let's see an example of this and kind of prove that this in fact does really work here. And we'll use the sine series expansion, so I'll justify that one to you with a nice plot. This is a plot of the sine function, and we'll look at what this is the Taylor series expansion is going to be for different orders of the Taylor series, the value n, or the maximum expansion. So if you consider the sum of the 0th order term of the Taylor series expansion for the sine function, you get that it's 0. So in blue here, you see the constant blue line here that corresponds to the 0th order term in the Taylor series expansion for the sine function. If we go up to the 1st order term in the Taylor series expansion, you have one term in the Taylor series expansion, which is the first term, and it's the power x to the power 1. So it's a linear term in the Taylor series expansion, and you get that it's exactly actually the tangent line. It's the best tangent line at the expansion point of 0. If you go to the second term in the Taylor series expansion, the next term up, you also have that line because the next term up is a coefficient of 0. If you go to the 4th term in the Taylor series expansion, or n equals 3, you get the next term up in the Taylor series expansion for the sine function, which involves a cubic. And if you continue this process of going to higher and higher and higher orders, you see very clearly that as you get higher and higher and higher, the infinite series expansion is getting closer and closer and closer to the actual value of the sine function around the expansion point, which is very, very cool. So we'll leave it on this one right here. This is when you go up to n equals 11 in the series expansion. But what you're seeing is as you go to higher and higher and higher orders in the series expansion, around your expansion point, the infinite series expansion, which is this blue curve, is actually converging to the sine function, which is actually amazing. It's really, really amazing because the sine function always stays bounded between -1 and 1, and what we're seeing is that this infinite series is converging to the function itself. If you change the expansion point, which is this point A, they're calling it in this Desmos applet, you get a different series expansion. So this is, say, change A, the expansion point, to 7. So this is expanding the function around x equals 7, which is right here. You see that the series is still converging and will still converge. Now, if you do 7 as your expansion point, you're going to get slightly different coefficients for the Taylor series expansion. But what's amazing is that it still converges around 7, and the radius of convergence of this series is infinity. So if you take the infinite sum, it will converge exactly to this sine function, which is incredible and very, very useful in many, many different applications in mathematics, in physics, and in engineering in general. So in terms of getting a series expansion, there's many, many tricks that we can do and many things that we can do to help us get the Taylor series expansion for more complicated functions. For instance, the natural log function, you have f of x is equal to the natural log of 1 plus u, or we'll do 1 plus x. The Taylor series expansion of this function of 1 plus x, or natural log of 1 plus x, if you go through and try to compute it, you run into a little bit of a problem, because the derivative of ln of 1 plus x is going to be 1 over 1 plus x. The second derivative then is going to be the derivative of 1 over 1 plus x, or the derivative of 1 plus x to the -1, which is going to be negative 1 over 1 plus x squared times 1 by the chain rule. So the third derivative then of this function is going to be the derivative of 1 plus x to the -2. So it's going to be -2 times -1, which is 2 over 1 plus x cubed then times 1 again, and so on and so forth. So the derivative changing here a little bit more complicated. It's not a huge problem, but it's a little bit more of a problem. But at the point, the expansion point, which we'll take the expansion point to be 0 again, you get that f of 0 is going to be the natural log of 1 plus 0, which is the natural log of 1, or 0. F prime at 0 is going to be 1 over 1 plus 0, which is 1. F double prime of 0 is going to be -1 over 1 plus 0 squared, which is -1. F triple prime at 0 is going to be 2 over 1 plus 0 cubed, which is 2, and so on and so forth. So the pattern is not as straightforward. We want to kind of get an idea of what's going on here. So let's do one more derivative. The fourth derivative, so f quadruple prime of this function at x. This is going to be equal to 2 times -3, so it's -2 times 3 over 1 plus x to the 4th times 1 from the chain rule. So at 0, f quadruple prime at 0 ends up being negative 2 times 3, or negative 6. So if you continue this process, you should see that the kth derivative in general of f, if you continue this all the way down to some positive fixed value k, is going to be k minus 1 factorial times negative 1 to the k plus 1 over 1 plus x to the k times 1. We don't have to write the times 1 if we don't want to. Which gives us that the kth derivative in general at 0 is going to be k minus 1 factorial times negative 1 to the k plus 1. This is giving us this oscillating term. And this is also starting at k equals 1, because at k equals 0, the value of the function is 0. So this means, using our formula, our Taylor's formula for the derivative, that ck is going to be the kth derivative of the function at the expansion point divided by k factorial, or it'll be k minus 1 factorial times negative 1 to the k plus 1 divided by k factorial. And k minus 1 divided by k factorial, because k factorial is the same thing as k times k minus 1 factorial. When you do k minus 1 factorial divided by k factorial, you're left with 1 over k. No factorial, just 1 over k. So this is the simplified form for the kth coefficient of the Taylor series expansion for the function 1 plus x. So ln of 1 plus x is equal to the summation from k equals 1 to infinity of negative 1 to the k plus 1 over k times x to the k. And this is the first example where our radius of convergence is actually not infinity. The radius of convergence for this series ends up being a finite value, so we have to be careful, because this is only valid, this equality is only valid when we're inside the radius of convergence, whatever that ends up being. So in this case, for this example, the radius of convergence is the limit as k goes to infinity of ck over ck plus 1, which is the limit as k goes to infinity when we plug in of 1 over k divided by 1 over k plus 1, or the limit as k goes to infinity of k plus 1 over k, which by L'Hopital's rule ends up being equal to 1. So this equality is only valid when x is strictly, absolute value of x is strictly less than 1, or in other words, when x is between negative 1 and positive 1. This series is absolutely convergent when this is the case, when x is in this value. So this is a good example because it shows that you don't always have an infinite radius of convergence. You have to be very careful when using a Taylor series that you're actually using the Taylor series inside the radius of convergence, because if you're not using it inside the radius of convergence, you could be trying to use something that's mathematically incorrect. Another example, you can consider the arctangent function. So the derivative of the arctangent function is 1 over 1 plus x squared. The derivative of the second derivative of the arctangent function, or the derivative of this expression, is going to be 1 over negative 1 over 1 plus x squared times 2x. And we see very clearly that there's actually a big problem here, because we can do more and higher and higher and higher derivatives of this function, but even this is relatively complicated. If you try and do the derivative of this now, you have to use the quotient rule, which will end up giving you something even more complicated, and that's going to keep happening for every derivative that you take of the arctangent function. So the idea is that we kind of want a more clever way of doing this, of figuring out this series expansion. And the way forward for us is to use what we already know. Specifically, we know that the geometric series expansion for, say, anything, 1 over 1 plus u, say, 1 over 1 minus u, this is equal to the summation from k equals 0 to infinity of u to the k when, and this is important, when the absolute value of u is less than 1. So we can use this whenever, for any variable, any value, as long as any value u, as long as u is less than 1. And if you look at this f prime here, right, f prime 1 over 1 plus x squared, this looks a lot like 1 over 1 minus u. It's not exactly 1 over 1 minus u, but if we rewrite this as 1 over 1 minus negative x squared, and we call u negative x squared, then this expression right here is the same thing as the expression, the sum from k equals 0 to infinity of u to the k, or negative x squared to the k. And this is valid when the absolute value of negative x squared is less than 1. And this is just applying our geometric series formula that we had before to directly use the geometric series if our function looks like a geometric series. And this is something that you can generally do. We can generally just plug in to find the Taylor series expansion for a function if it looks similar to another function, but you have to keep in mind the radius of convergence condition. So this is saying that when this is true when the absolute value of x squared is less than 1, or when the absolute value of x is less than 1. Right, so this equality right here, these two things are equal to one another whenever the absolute value of x is less than 1 by the geometric series. So what we've shown is that the derivative of the arctangent function which is 1 over 1 plus x squared, is in fact equal to the infinite series from k equals 0 to infinity of negative 1 to the k times x to the 2k for all points where the absolute value of x is less than 1. And the last step in this process is we're looking for the Taylor series of arctangent of x. So this Taylor series is for the function 1 over 1 plus x squared, the derivative of arctangent of x. So what we have to do is integrate both sides, which we can do using term-by-term integration. Because our theorem at the end of the last lecture showed that if we take you can take the integral of a power series inside the radius of convergence, we can go through and directly determine the integral by doing term-by-term integration, as long as we're within the radius of convergence. So the antiderivative of arctangent of x, the derivative or the antiderivative of 1 over 1 plus x squared, is the antiderivative of the derivative of arctangent of x. So this is going to be just arctangent of x. And the antiderivative of this sum, this summation, this infinite summation, is going to be the sum from k equals 0 to infinity of the antiderivative of this entire expression. And then plus some integration constant d. So arctan of x is going to be equal to the summation from k equals 0 to infinity of negative 1 to the k over 2k plus 1 times x to the 2k plus 1. And this is the correct Taylor series expansion for the arctangent function. So this is a very, very powerful tool. You know, the idea here is that being able to take an infinite series expansion and replace a function with this infinite series allows us to do a lot of very kind of clever things in many aspects of engineering, in physics, and also even in pure mathematics as well. So it's a very remarkable idea and a very powerful idea. But that will conclude the lecture for today. Thank you very much for watching the lecture. I hope you learned something.